So today we're very happy to have Kirchhoff-Lukat, who will tell us about log intersection Floer cohomology for logs and collecting surface.
Yeah, thank you very much for the invitation. So in addition to the title that I originally gave, which is the specific project that I'm working on right now, I now put this more general subtitle where to basically give some context to this project. So this is research part of my current big research project for steps in neurosymmetry for generalized complex geometry, which so I have a grant from the European Union to study this. And so that's the context or the big motivation behind my project. So I'm going to start by basically talking a little bit about the general idea behind the project before going into details. So the motivation for this research is to at some point get to essentially extending neurosymmetry, which as it's currently known is a duality between possibly Calabi-Yau manifolds, or if you want between complex and symplectic structures, to some specific contexts in generalized complex geometry. So maybe first for some historical overview. So neurosymmetry is this idea that originally comes from string theory, where physicists observed that what would sometimes happen is if they had a string theory that was defined in terms of the symplectic structure of one Calabi-Yau, that would be physically the same, so give the same physical states as a string theory on another Calabi-Yau equipped with a complex structure. And well, to start with, this was just a thing in physics, but then mathematicians got really interested in it after Philip Candelas and collaborators employed the mirror symmetry on Calabi-Yau manifolds to essentially predict counts of algebraic curves inside Calabi-Yaus, which before so mathematically had really, people didn't know how to do it, or it was really difficult. And they, using mirror symmetry, so using the symplectic side, they managed to make predictions that were later proven to be true. And so this is what got mathematicians excited about this. And so one of the mathematical approaches to mirror symmetry that's certainly very popular today is homological mirror symmetry, or HMS, which is used in Savage. Famous work in 1905. And the idea here is again to relate the symplectic geometry of one manifold to the complex geometry of another manifold, and in this case by establishing an equivalence of a infinity category. So on one side, the symplectic side, we have the prior category. On the complex side, we have the derived category of conversion. So I'm not going to talk about the specifics all that much. Okay, so it turns out that when you do string theory, you can formulate consistent string theories not only for symplectic or complex backgrounds, but for more general geometric structures that are somehow hybrids of complex and symplectic. And this was already known for a while before really the consistent mathematical description of these was given. But since then, I mean, especially since people started mathematically describing generalized complex geometry, certainly this has taken off also in string theory much more. So in mathematical terms, you can formulate a consistent string theory when the background of the spacetime manifold is a particular generalized complex manifold. so certainly that's one of the motivations why people are interested in generalized complex geometry. So this is a relatively new field. This was started by Nigel Hitchin and then some of the students in particular, Marco Gualtieri, later the Cavalcanti. Sort of from about 2003 onwards. And so generalized complex structures are more general geometric structures that encompass both complex and symplectic geometry, and that can be used to formulate consistent string theory backgrounds. And so certainly a natural question is whether mirror symmetry extends to generalized complex geometry in some way. Now, yeah, this is a very general question, and certainly neither mirror symmetry nor generalized complex geometry at this point seem to be sufficiently understood to just, do it in full generality. So, but there are a few specific contexts where I think things can be done, and so that is the goal of my work. So let me briefly say what generalized complex structures are. So from now I'm going to abbreviate it to GC. So generalized complex structures fit within this whole framework of generalized geometry, which basically in the simplest or more general terms means doing geometry on Tm plus T sub n. So ordinary geometric structures are usually defined just on Tm, and now here the idea is that we basically extend this by summing it with the full vectors. And at the beginning this might look a bit random, but the structures that we naturally find when doing this turn out to encompass a lot of, ordinary geometric structures and generalize them, as is the case for generalized complex. So a generalized complex structure on manifold M is an endomorphism. I'm going to note by basically curly J of this direct sum with the following properties. First of all, J should be orthogonal with respect to the natural canonical symmetric bilinear form that is on this bundle. Namely, we can always pair two elements. So an element is composed of a vector part and a one-form part, and we can always bilinearly pair these by just sticking the vector part from one side into the one-form part on the other side. So like this. This is a split signature bilinear form. So if the dimension of M is n, then the rank of this bundle is 2n, and the signature of this is n. Okay, so we require orthogonality. Then we also require that this endomorphism square to minus the identity. So here you can already see this looks exactly like an almost complex structure just on the tangent bundle. And so this is then basically what we would call an almost generalized complex structure. And then we have an integrability condition, just like for ordinary complex structures. And that is also basically the same, which is that the plus I eigenbundle, which is a subbundle of the complexification, should be integrable. So, with respect to what is basically an extension of the Lie bracket on vector fields to this bigger bundle, namely, so it's called the Dorfman bracket or just Dorfman bracket, and it looks like this. So the vector part is just the Lie bracket, but then there's a one-form part, like this. Now you will notice that this is not actually the contrast to just the Lie bracket. This is not antisymmetric, but it is almost so in that the symmetric part is exact. So the symmetric part of this is expressed in terms of this bilinear form. Like so. And this bracket does obey a form of Jacobi identity. So it's not a Lie bracket, but it is close enough that you can work with it nicely. So what do I mean is integral with respect to this? I mean that the sections of the plus I eigenbundle should be closed under this. And this is really a very obvious generalization of complex structures into generalized complex context. If you take an endomorphism of the tangent bundle that squares to minus the identity and whose sections are closed with respect to the Lie bracket, that's exactly what a complex structure is. So here we've just taken that and ported it to Tm plus T star m. So some examples, you can get a feel for it. So if we have a complex structure, so endomorphism of the tangent bundle, then that had better be generalized complex, and it is. So if I write a block matrix like so, where you imagine this block matrix like acting on Tm T star m like this, right? Then this is generalized complex. On the other hand, I've already basically made a spoiler and said, wait, maybe I shouldn't write this, I should maybe write the other one. Oh, there's a third chord. So I already spoiled it and said that symplectic structures are also generalized complex. So how does that look? I can again write such a matrix, but now using the other entries. So then this is generalized complex. And in this way, basically, complex and symplectic geometry are the two ends of a generalized complex spectrum, where in general, generalized complex structures will interpolate between these in the following way. So for a general structure, I won't really know what these three components are, but I always have this component that goes from T star m to Tm, and the conditions that I gave for the definition of a generalized complex structure imply that this is Poisson. So the Poisson bivector, i.e. it is antisymmetric, and it induces a Poisson bracket on the function so that those satisfy the Jacobi identity. So in that sense, generalized complex structures are basically a subset of Poisson structures together with extra data. And what is the extra data? So the Poisson structure foliates M into a symplectic foliation. That is a property every Poisson structure has. And then the generalized complex part is that on the transverse directions to the symplectic foliations, there will be a complex structure. So locally, at least around regular points, so where the rank of this thing is regular, this is always isomorphic to some complex vector space with product the standard symplectic vector space. And the dimensions of the complex space and the symplectic leaves, they can of course vary across the manifold. So you know, Poisson structures can be singular, they can jump in rank, and so can this. Yeah, this rank here, the K, is a local invariant. That's called its type. So type of J is equal to at a point, so type of J at P is 1/2 the dimension of M minus the rank of phi. And so what can we have? The minimum rank, the minimum type is 0. That is when, well, it's all symplectic, right? In that case, the local type is 0. And then the maximum is n, where dimension of M, real dimension, of course, is 2n. So basically half the dimension is the maximum type, and that is when the manifold is fully complex. And then, you know, it can interpolate in between. The type can only jump within the same manifold in even steps. So globally, the type of a generalized complex structure is either even or it's odd. And the generic situation is always that the type is minimal. So the generic even type generalized complex structure will be type 0 on a dense set and then have a type jump locus of a lower dimension. And similarly, for odd types, generically the type will be 1, and then again can jump up to 3, 5, so on lower dimensional submanifolds. Yeah. This is the definition of type, yeah.
Okay, so
But this is equal to the K that I wrote here.
So it's the complex dimension.
Yeah, exactly. Yeah, exactly. That's exactly it. Yeah.
Okay.
So now I'm going to talk a little bit about a particular subclass of generalized complex manifolds that are called stable generalized complex. And this is basically the nice case of the generic even type. So as I said, in even type, generically the manifold will be type 0. And so here we look at even type, smooth type jump locus, so it just jumps up on a smooth submanifold. And only jumps up to type 2. So what this looks like is we have the manifold, it's 2n dimensional, and then we have a codimension 2 locus in there, generally called D, that is 2n minus 2 dimensional, and where the type jumps to type 2, and the D is smooth. So in the compact case, this actually puts pretty strong restrictions on the topology of D. So I'm not giving you the precise definition, this is just basically how it looks. And let's say as an example, if it's a 4-manifold, so in the 4-manifold case, what you get is a symplectic structure in the bulk, and then it jumps up to type 2, which for 4-manifold means complex. So you end up with this type change locus that's real 2-dimensional. There is an elliptic curve. So a torus with a complex structure. So that's how these look in 4 dimensions. Okay, this is to write this down. So the study of stable generalized complex structures, that's first due to cover Kantian theory. And so why are these a class of manifolds we want to look at? So there's a few different reasons. The first is that, so when people started studying generalized complex geometry, they didn't really know if the class of generalized complex manifolds was any bigger than just symplectic and complex manifolds. So that wasn't known. And stable generalized complex structures provide the first example of a manifold that admits a stable GC structure, but does not admit complex or symplectic structure. And so there are actually now a bunch of examples, but basically the simplest one is odd connected sums of CP2 with itself. So, for example, 3 CP2s stuck together with a connected sum, where connected sum means we remove balls and glue them along the edges. And so the way to prove that this is neither complex nor symplectic is as follows. So for complex surfaces, this is a compact like form manifold. So if it was complex, it would be a complex surface. But those are classified. So there's the Kodaira classification. So you can check that this doesn't fit into anything in the Kodaira classification, so it can't be complex. And for symplectic, you check its Seiberg-Witten invariance. And there's one Seiberg-Witten invariant of this that can be computed to be 0. But for symplectic manifolds, it would need to be non-zero. So this admits neither of that, but it does admit a stable generalized complex structure. And so Cavalcanti and Gualtieri specifically constructed this. So that's one reason. So mu. And then another reason is that up to a certain type of gauge equivalence, these stable GC structures are actually determined by this Poisson structure here. So the complex bit doesn't really play a role, at least not up to gauge equivalence. And so this Poisson structure will be, symplectic in most of the manifolds, and then go to lower rank on the degeneracy locus. But up to a gauge equivalence, it determines the whole generalized complex structure. And now, if we're interested, as I originally motivated, in extending ideas from mirror symmetry to generalized complex geometry, then this is an attractive starting point. So we know how to, construct the Fukaya category, which is the symplectic side for symplectic manifolds. And this is a manifold that's still symplectic almost everywhere, and it only has this degeneracy locus sitting in there, and it's a nice type of degeneracy locus. So the way the degeneracy that chi has is of a specific, pretty nice type. And so the hope there is that we already know that for stable generalized complex geometry, there are quite a number of results that can be extended from just symplectic to this context. And not everything, but there are a number of things that we can extend. And so the hope is that we can go and construct a Fukaya category for such manifolds. And so that's what I'm hoping to do. However, that's not right away where I started. So Fukaya categories, for their definition, use concepts of pseudo-holomorphic curves and Lagrangian intersection Floer cohomology that have a very complicated analysis. So there are a lot of analysis issues around. However, if you go to real 2 manifolds, so real surfaces, the analysis issues all drop away and things become combinatorial. So when you're trying to understand how to extend things to a slightly more general context than just symplectic, it's attractive to first do it for real surfaces. However, so there are really, for dimensional reasons, the generalized complex structures on real surfaces aren't really that interesting. So it is convenient to go to something that isn't generalized complex, but still pretty similar in that it's also a Poisson structure with a particular nice degeneracy. And these are called log symplectic. And so that's what I will talk about for the rest of this. So basically, I call this toy model. Which section number am I at? 3. So 3 is the toy model for stable generalized complex, and that is log symplectic surfaces. So Log symplectic geometry works in all, well, even dimensions. So in general, a Poisson bivector on an even dimensional manifold is log symplectic if its top power, so the nth power will be in the top power of the tangent bundle, intersects the zero section transversely. So the top power vanishes linearly, basically. Like this. So in the case, so what this implies, first of all, is that pi is everywhere non-degenerate, because this is the determinant of pi. So it's everywhere non-zero, except on a codimension 1 submanifold that is smooth. So you can see that this is pretty similar to over there, except we're now looking at a degeneracy on a hypersurface instead of a codimension 2 submanifold. But it's still a case where we have a manifold that's mostly symplectic and then just comes with a nice degeneracy. And these are pretty widely studied in Poisson geometry. So when doing Poisson geometry, studying general Poisson structures is often frustrating because a Poisson structure is a very general object. But then again, this is a nice class that you can somehow get a handle on and where you can say a lot. So in dimension 2, which is what I'm interested in here, this is just a surface. So and we're going to restrict to oriented surfaces. There are non-orientable ones with such a structure, but so we're going to stick to the oriented case. So oriented surface with bivector. And now the condition here is just that the bivector itself vanishes transversely, and it will vanish on a collection, finite collection of disjoint circles in the surface.
Just a quick clarification.
Yeah.
You're not requiring the vanishing locus of the top power of the bivector to be reduced, right? So you're not requiring that pi to the end define this codimension 1 locus in a allow it to define that locus with multiplicity, at least as far as I can tell from the definition.
This should imply that it really is no multiplicity because of the transverse vanishing.
Oh, it's smooth, so
Yeah.
Okay.
Yeah, it's
okay.
smooth.
Okay.
Yeah.
Yeah. Okay.
Yeah, so also in
You're
this
right.
case, yeah, so in the complex case, you have to be, so basically in the complex case, which this, if you want to, you can do this as a kind of complex log symplectic thing, and there then, yeah, you have to sort of, there are certainly interesting things to be done where you include normal crossing of the thing with itself.
Yeah.
But here, not so much. This is
You're absolutely right. All from what you. Oh, thank you.
yeah. Yeah, let's put this here smooth. Right, so okay, so in the surface case, what we get is this bivector. So Poisson structures on surfaces are easy because any bivector, for dimensional reasons, induces a Poisson bracket. So the Jacobi identity is automatic. And so we just require that this thing only vanish on a basically finite collection of disjoint circles. And so these things basically started the study of log symplectic geometry, and they are classified. They were classified by Olga, which is one of the few instances in Poisson geometry where a class of Poisson structures is actually classified. And so that's another thing that's attractive about these. And so I'm basically briefly going to write down Olga classification. So First of all, you need the topological arrangement of vanishing circles up to orientation preserving diffeomorphism. And actually, the vanishing circles are oriented. Then to each vanishing circle, there's an associated positive constant that's called the modular period. And for people who know Poisson geometry, this comes from integrating the modular vector field along the vanishing circle. So we're going to call this gamma I. And then there's essentially a generalization of the symplectic volume, which Ratko calls the regularized viewable volume. So this is a real number, so that can also be negative. And that is relative to basically a chosen orientation of the surface. So we're always assuming that we've chosen an orientation, and then we also choose one of these types of Poisson structures. So around each circle, you can find local coordinates that put the bivector in a nice form. So if the local coordinates are x and theta, this is basically what the bivector looks like. So here's the vanishing cycle gamma I, and then theta is the coordinate along this cycle, x the transverse coordinate, then you get this linear vanishing, and here this basically, I mean, okay, it depends on how you normalize it, but then basically you can have this as related to the modular period. And so tau is the modular period, and these are related in that way. So that this is what they look like. And so you can see these are, of course, much more complicated than just symplectic surfaces. So symplectic surfaces are classified just by their viewable volume. So just has a symplectic volume up to symplectomorphism. But here, I mean, it's still, this is a set of complete invariants, and it's not that complicated. So I have rephrased this classification a little bit, which I mean maybe makes things a tiny bit clearer. So basically, what you can do is to each such structure, I'm going to draw an example. So let's have on the genus 2 surface, let's have a pi with these kinds of vanishing circles. Then each vanishing circle has a period. The thing has an overall volume that I'm not going to write right now. But then relative to the global orientation that we've chosen, each of the symplectic components also comes with a sign, depending on whether the symplectic form of the component has the same sign as the global orientation or the opposite. So for example, it could look like this. And the fact that the sign always have to jump when passing through the vanishing circle already tells you that not all configurations of curves will lead a structure that is compatible with it. Which ones do? Well, the ones that are associated to bipartite graphs. So bipartite graphs are those graphs where each vertex, so where you can do a two coloring on the vertex. So where you can assign signs to each vertex such that if you pass along an edge, the sign changes, which is exactly what I just said, right? So to this surface, each symplectic component is a vertex. So we have 3 vertices. Each circle is an edge. So this is what the edges look like. And then we have signs associated to each vertex and real numbers associated to each. Signs to each vertex and real numbers to each edge. And then we have the global volume as well, which I'm sort of leaving out here. And basically, this is what you do. So you take a bipartite graph, equip it with the two coloring and these positive numbers on the edges, and then whoop, you can go and get a log symplectic surface. Okay. How far along? 20 minutes roughly? Or 25? 25. Okay, cool. talk a little bit more specifically about constructing the Fukaya category, or at least defining Lagrangian intersection cohomology. So, okay, again, I don't really know who's in the audience and how much people know about homological mirror symmetry, so I'm briefly going to say what the symplectic side of homological mirror symmetry is, which is this Fukaya category. I'm only going to say what it is roughly. So, as objects, it has a certain class of Lagrangian submanifolds of a symplectic manifold. So, and potentially the Lagrangians are equipped with an extra structure, and potentially there are conditions on what Lagrangians we should pick here. For example, I mean, in a compact symplectic manifold, you would always do compact Lagrangians that have some additional conditions potentially. And then as morphisms, we have what's referred to as the Floer complex, which is a fancy name for basically the formal direct sum over all intersection points of the two Lagrangians. And here we need to assume that the Lagrangians intersect transversely so that they have a finite number of intersection points if they're compact. So we sum over all those, and it's basically just the free module over these. And okay, I'm going to say it's over some field K. For this talk, K will always be just Z2, but potentially it's something more complicated. It's a more complicated field. So formal sums of intersection points is what the morphisms are. And yeah, well, this looks funny at first, but I'm going to say in what way will make sense. So this is not, as I've written it, this is not exactly a category. So there is a way to compose morphisms. So we now need to give a way to compose intersection points or sums of intersection points. But this is not associative. Instead, it's associative up to some higher operation. So people might have seen A-infinity algebras around, which basically this is the categorical version of an A-infinity algebra. So instead of having an associative multiplication, you have a bunch of different compositions that obey relations that basically for the composition amount to associativity up to higher terms. And in particular here, there's a way where you can take cohomology to get an actual category in the usual sets. So yeah, what we have is these composition maps. There's one for every natural number that take, so mu k takes k morphisms. So these need to be composable. And then so the form from L0 to K like this. And so we are mainly interested in the lowest two. So mu2 is the composition that one would expect to have. But mu1 is also very important. So mu1, which then just goes between, so from L2, L1 to itself. And this is actually a differential. So this is denoted by del, usually squares to 0. This is a non-trivial condition. So it squares to 0 precisely when we've chosen the right class of Lagrangian submanifolds. And this is often non-trivial. So you usually can't take all Lagrangians or even all compact Lagrangians. You need to restrict further in order to make this be a differential and square to 0. And yeah, this is what's called the Flow differential. So how is that defined? I'm only going to define it for this easy context of surfaces that we're looking at. And first, I mean, it's going to be basically the same in the log symplectic case, but for simplicity, just assume things are symplectic. So in a surface, again, for dimensional reasons, any one-dimensional submanifold is a Lagrangian submanifold. You know, so two forms pull to zero on one-dimensional things. So a priori, every one-dimensional submanifold in a surface should be considered as a candidate for an object in the required category. And so if these intersect transversely, we'll get nice intersection points. And the differential of a single point is defined as follows. So we sum over all other intersection points, Q, and then the factor weighing each Q is the number of what's referred to as smooth loons, or if you want, smooth strips, smooth disks from P to Q. And what are these? So here's one Lagrangian L0. Here's the other one. Here's the point P. Here's the point Q. And then this kind of half-moon shaped thing that lies in between the two Lagrangians, with the endpoints being precisely the two intersection points. That's what we call a smooth loon from P to Q. And here it's important that the corners are actually convex. So convex corners. In high dimensions, there is something called the Maslov index that one needs to count. And so that you can define that here, and then saying that this has the right index is basically saying that the corner should be convex in this case. And so again, it's non-trivial that this thing squares T0, but in this case, you know, it's purely combinatorial. You're just counting these funny disks, and yeah, it does square to zero. And yeah, so again, I'm not going to explain Lagrangian intersection Floer cohomology in 2 dimensions very precisely, but what I want to talk about now is what changes when we pass from symplectic surfaces to log symplectic. So for the symplectic case, there's a monograph by Silva, Robin, and Salomon, where this is basically laid out how to do it. And yeah, I'm building on top of that and extending it to the case where the Poisson bivector can vanish on a collection of circles, as I've described. Wait, this doesn't go up. Okay, let's. So since the structure is symplectic away from this vanishing locus, what we're really interested in to get aware somehow either the problems or if you want the interesting new stuff comes up is when we have submanifolds that intersect with that. So L. Oh, I've gone from calling it Z. Okay, I'm still calling Z the locus where the vector vanishes, which might be decomposed in general of multiple stuff. So that's different. What I guess I didn't say here is that when we choose the objects, so really the objects are equivalence classes of Lagrangians up to Hamiltonian isotopy. So we should consider 2 Lagrangians the same if they can be related by Hamiltonian isotopy. And that, for example, immediately solves us the problem when 2 Lagrangians don't intersect transversely, because what we can do then is perturb one of them with a Hamiltonian isotopy so that they do. And in particular, this allows us to define you know, homomorphisms of the Floer complex for Lagrangian with itself. We perturb it by Hamiltonian isotopy, and then that's what we mean by saying, okay, this is the Floer complex for Lagrangian with itself. And this is okay to do because while the chain complex here, of course, does depend, like that can change when we move it with the Hamiltonian isotopy, the cohomology of the complex will not. So this is an important theorem by Floer that the complex changes, but the Floer cohomology is actually an invariant of the Lagrangian. Okay, and so here now, when we go to log symplectic surfaces, we should also consider Hamiltonian isotopies. And now with Z actually being a vanishing thing, here there is something that changes. So every Poisson structure has Hamiltonian isotopies. So they come from integrating Hamiltonian vector fields. And this is what a Hamiltonian vector field for function H looks like. So in particular, you can see that these will always vanish on Z. Which means that any Hamiltonian isotopy restricts to the identity on Z, i.e. intersection points of a Lagrangian with the vanishing locus can never be moved, they are fixed. So as soon as two Lagrangians have different intersection points with Z, they will be different in the prior category. And in some way, so compared to just symplectic surfaces, in some way this gives you more different Lagrangians because you can't move them around as much. So identity. So relevant isotopies don't move and so even though it is, so we want to consider the surface as a compact surface with the circles marked on it, you can sort of see that the symplectic part of the surface is now suddenly no longer compact because the symplectic part is M with Z removed. And so it should come as no surprise that when defining Lagrangian intersection Floer cohomology, some phenomena that usually come up in non-compact symplectic manifolds arise here as well. Namely, so what happens here is that the Floer complex between two Lagrangians, so now suddenly switch to calling them alpha and beta, is asymmetric. And this happens because in order to make this well defined, we now can no longer use all Hamiltonian isotopies, but instead only specific ones. And we say that, so really what we want to do is always consider the Floer complex from A, and we move B with time 1 Hamiltonian isotopy, where we only allow specific Hamiltonian isotopies, and that makes this asymmetry appear. Why is this necessary? Otherwise, so we need the Floer cohomology to be invariant under the class of Hamiltonian isotopies that we've chosen. And in order to achieve this here, and in many cases where the symplectic manifold is non-compact, well, we need to basically say, okay, we only pick certain Hamiltonians. And then this asymmetry shows up. So I will go into a little bit more detail how that happens.
Can I ask the question?
Yes.
So you're doing you're looking at Hamiltonian isotopies where the Hamiltonian is a C infinity function on the whole manifold and you're not allowing it to go to infinity at C.
No, it's a C infinity function on the whole manifold. And in a second, I'm going to write down which ones you take in order to make the cohomology invariant under Hamiltonian isotopy. So should I just write that down and maybe they will answer the question? So
yeah, so these are very different than the moment maps one typically sees in the toric geometry. These are very different to the moment maps that one typically sees in the Hamiltonian geometry of B-symplectic manifolds or log-symplectic manifolds. Those usually have logarithmic singularities along Z. So
yeah. So no,
but this is quite a different.
Here we do not want to allow that.
Okay.
So in fact, we only want to. So remember that I had this local coordinates here, which were on a cylindrical neighborhood of the vanishing circle. I had these coordinates x and theta, so that basically the modular vector field is c times delta theta. And so, yeah, this delta theta direction, that the direction is actually given by pi. The direction is given by the modular vector field of pi. This is why each vanishing circle comes equipped with an orientation. And basically, so if this is the circle, modular vector field goes in this direction. We will always choose this x theta so that it looks like this. And the Hamiltonians we allow, I guess, yeah, this can depend on theta. Should look like this, and this has to be positive. So basically, the Hamiltonian isotopy, what this will do, if the Lagrangian starts out like this, then what this will do is move it to something like this, near the vanishing circle. So where x is positive, so x goes in this direction, so where x is positive, it moves it up. Where x is negative, it moves it down. This becomes important as soon as we're interested in the Floer complex of two Lagrangians that share an intersection point with Z. So if the intersection point sets with Z are disjoint, then somehow the issue doesn't come up. But as soon as we have a situation, let's say for the log-symplectic disk, where we have two Lagrangians alpha beta that share this intersection point, it is important that we do this. So according to this rule, where I said they were always going to perturb the second Lagrangian with such a Hamiltonian isotopy, when we look at CF of alpha beta, what we really mean is this. Whereas for CF beta alpha, we now perturb alpha. So we get this, and you can see that these are fundamentally different in terms of the intersection points that they have. But if we use this definition, then what we get is such that the cohomology of these chain complexes will be invariant under all, for the disk, all isotopies that fix the endpoint, which on the disk, so all Hamiltonian isotopies that fix the endpoint, basically locally, basically all of them, that means all of the isotopies. Right, so that is what we need to do here in order to make this well defined, and this is the same thing that comes up in, for example, the wrapped Floer cohomology for Liouville manifolds, non-compact symplectic manifolds, and actually what I'm currently in the process of showing, but I'm very confident is true, is that if we have a manifold that is just one symplectic component with the log boundary, such as, for example, this disk, and we remove the boundary, then the Floer cohomology that is just defined is the same as what's called the infinitesimally wrapped Floer cohomology. But of course, so in general, we won't just have this with a boundary or some surface with a boundary, but we will have a surface with multiple symplectic components. And that's where one last really interesting phenomenon appears, namely that while we can never have disks, so we can never have disks that go from a point in the boundary to anywhere else. So that's a rule. Disks never end or begin, in Z, so they never begin or end in the vanishing circle. But you can have disks that pass through it, and I will make an illustration of how that looks. With a fairly easy example. So let's do an S2, and let's do the easiest log symplectic S2, which just has a vanishing circle on the equator with the modular vector field going in this direction. So theta x, this has positive sign, this is negative sign. Let's look at this Lagrangian and consider the Floer complex of this thing with itself, meaning, okay, we now perturb it using one of the isotopes that I just hid behind this board, which looks like, so the perturbed Lagrangian will look like this. One sec. This, maybe here, this is the point where I should use color. Okay, so which intersection points we have? We're going to call this one up here P1 and this one up here, down here P2.
You want to use yellow or orange? Blue.
Yeah, I realize that that isn't really that visible. So I'll do orange for the loops. Okay, so intersection points here, outside the vanishing locus, and then we have two more intersection points that are in Z. I'm going to call those Q1 and Q2. Now I've already said that we never want to consider any loops that begin or end in Q1 and Q2. And there is basically an analytical argument as to why we don't want these. That has to do with, so in higher dimensions, the loons, well, what the higher dimensional generalization of that is pseudo-holomorphic disks. So they pseudo-holomorphic, they satisfy something like a Cauchy-Riemann equation, and the generalization of this to this case with the vanishing Poisson structure on Z basically means that, yeah, you don't, like, solutions that go to Z or come from Z won't have finite volume, so you don't want them. However, because these two halves have different signs, the sum of these two will be finite. So there's a regularized version of the sum of these two. And so what you can have here is what I refer to as a broken loop from P1 to P2. Del P1, so there's a broken loop here. And then actually there's another one on the back, right? This thing is somehow symmetric. There's this other one that's on the back side of the sphere. So we actually get P2 again because we've been working over Z2. This is 0. So sorry, still a pretty boring complex, but it's important that yeah, to see here that this differential is non-trivial, and it is non-trivial with like having these broken loops in there. Well, and then so with chosen orientations of the Lagrangian, from the orientations of the two Lagrangians that you're considering, you can assign degrees to the intersection points. So if you're working over Z2, then the degrees are only up to Z2, but since we're in 2 dimensions, we will only have degree 0 and degree 1 anyways. So this is a degree 0 point. And this is the degree 1 point, as it should be, right? You know, differential increases degree. For reasons that, so for basically reasons that right now are not 100% clear to me, the intersection points inside Z should also be degree 1. And then the Floer homology of L with itself, or what they call alpha, so Floer homology alpha with itself, in that case agrees with what's called the log homology of alpha with respect to the intersection with Z. So I'm not going to explain exactly what this homology is, but whenever we have a manifold with a marked codimension 1 submanifold, so specified codimension 1 submanifold, then the log homology is the natural homology associated with this. And so what we find here is that this, like the Lagrangian intersection Floer homology as I have defined, will reproduce you the log homology of the submanifold relative to its intersection with Z, which is what you should somehow expect to get for this scenario. And so that's a strong indication that this is the right Floer homology to consider here. And so of course I haven't proved this for you, but as I've said, in this scenario, the differential does square to 0. It is invariant under Hamiltonian isotopy, where you pick the particular class of Hamiltonians that are specified, so these specific ones. Yeah, and so this is how you define Lagrangian intersection Floer homology for a log symplectic surface. Now, when it goes to defining an actual Floer category, my hope is that well, basically the classification of log symplectic surfaces needs to be reflected in what you get for the Floer category. So you somehow have to be able to see the vanishing circles and the modular periods. And I think that, so how you see the modular periods, that is actually fairly clear, because Lagrangians cannot move their intersection points with that. Somehow where the intersection points land specifies the Lagrangian. So basically, if you want, here we have one big circle for each angle on this circle, which, I mean, I think that's how the modular period basically translates into the Floer category. But I have not finished that calculation specifically for any of the surfaces. But yeah, so my plan now is to basically look at what the Floer categories of these would look like, maybe see if there's any sense in having mirror partners for these types of surfaces, and then eventually apply the lessons that I have now learned from how to deal with a vanishing or degenerating Poisson structure. Yeah, lift that to the stable generalized complex case. Yeah, thank you for your attention.
Any questions?
Well, it kind of comes back to the question I asked. Which is that there's a more general definition of log symplectic in which the divisor is not required to be smooth, but can have normal crosses, and then you impose that it's defined in a reduced way by the vanishing of whatever appropriate power of the Poisson line vectors. If you worked in that kind of generality, how constrained?
And so I think that really for real log symplectic, this doesn't really make sense, right? Like for real log symplectic, as soon as you have this vanishing like transversely to the zero section, it is always that you always get smooth. But what you can do is, instead of,
I guess what it means is you wouldn't impose transversality. You would just say that the vanishing locus is
It's
reduced
normally,
and
yeah.
normal crossing.
So I guess in the real context, people don't consider these at all. So what is considered, and this is this is referred to as stable generalized complex with normal crossing. So there's some work by Kirchhoff-Lukat and on these, where so stable generalized complex structures, and this is something I didn't say, can basically be defined similarly to log symplectic, just in terms of the vanishing of the section of a complex vector bundle rather than the vanishing of the section of a real vector bundle, which this was here, right? Like the nth power of pi is a section of the top power of the tangent bundle, which is a real line bundle. And so instead, stable generalized complex can be defined by saying we have a section of some complex vector bundle that vanishes. And so then you can conventional stable generalized complex structures would still be defined in such a way that you assume the locus is smooth, but you don't have to. So in that case, it's very natural to pass to normal crossing. And you can do that, but as I said, it's somehow very natural to allow that, right? Because if you perturb the smooth ones a little bit, you might sometimes get normal crossing. So the thing is that this makes just the underlying Poisson structure already quite a bit more complicated, because the type jump will now, there will now be multiple different jumps of rank, multiple different degeneracies. So basically everything. So then somehow already, like, even though it's still pretty simple to write this down, this is already quite a bit more complicated, even in terms of just the Poisson geometry. So certainly when doing this for stable generalized complex, I would again first say, okay, let's do for smooth vanishing locus, because with the multiple type change locuses around, things become immediately way more complicated. For example, for the smooth vanishing locus for stable generalized complex, the deformations are very well understood, and the Poisson homology is well understood, and that already is way harder as soon as you allow normal crossings.
Sure.
So I guess so that's somehow where you get into this thing with Poisson geometry, where often as soon as you like broaden your class of Poisson manifolds slightly, suddenly a lot of things don't work anymore. And so I'm not sure. I mean, maybe so people are working on this normal crossing case, and because it's still like fairly nice, and so maybe people will be able to do a lot of things there. But one also needs to remember that even when I say stable generalized complex and the vanishing of a section in a complex line bundle, this is all still, so it's complex, but it's smooth. We're not in general not imposing holomorphicity conditions in any way. This is all still in the smooth category. And so things are not as rigid as they are in the holomorphic case. And so is that meant to go now? So I can't say what exactly would change. I would certainly, my goal is to do it with the smooth case, and if that works, I'm already very happy.
Other questions? Zero person? All right, well, if not, let's thank Charlotte for the nice talk again.
Yeah, thanks everyone for listening.